Okay, so let's continue our lecture for product quantization. Last week we already talked about the basic concept of product quantization. And you can treat it as a general technique for vector quantization. Okay, and so we talk about like PQ and OPQ. And also the very important techniques they use the k-means cluster to generate the codebook and then perform the quantization. And then we will use cluster centroid to reconstruct according to its code. Okay, so we already addressed some of these issues, including the how they save the memory and how they speed up the quantization and how to apply it to do index. Okay, so based on the product quantization, there are several variants. Last week we already introduced OPQ, it's an optimized product quantization. Okay, so now today we will talk about another variant derived from the OPQ. So the name is locally optimized PQ. It's called OPQ. Okay, so what's the OPQ? This paper is published in CBPR 2014. And in this paper, they say it's a very simple idea. The idea is you can perform the k-means clustering first to separate your data into several clusters. And for each cluster, you apply the OPQ individually. So the idea is it's very simple. So that's why the author said in their paper, they feel embarrassed about this topic because the contribution things were just a little bit. Okay, but the fact is this idea published in the top conference. Okay, so let's give a detail, introduce OPQ, and also we can take this chance to review the whole process of the PQ family, about the PQ family's techniques. Okay, so locally optimized, the idea is locally optimized product quantizer for per cell. Also, it means per cells, per cluster, and to encode their residuals. Okay, so how to compute the residual? So you just recall that in PQ, they applied IBF PQ. The IBF PQ is actually the same idea. Okay, first we compute the residual. It's given the vector x, and the x what is cluster below. Okay, based on a cross quantizer Q, so we can find where x should be belong to which cluster. And if x belongs to that cluster, you just subtract it to get the residual. So this is what we call the residuals. It uses the function R. And for all the data that are assigned to the cluster, to the cell I, and then we just collect all the residuals. We denote it as Zi. So all the data belong to the I cell, I cluster. Okay, we collect them and collect their residuals Zi, and then train a codebook by using OPQ for each cell. Okay, and in here you can find the OPQ is actually a hierarchical quantization. So because first you can think about there are two quantizers. The first one is a coarse quantizer to cluster all the data into small groups. And for each cluster, then you perform the PQ. This PQ is a second quantizer. So actually, you can can treat it as a hierarchical quantization. And with this, we consider that we can better capture the data distribution. And also, such a residual distribution is usually closer to Gaussian assumption. Okay, so this is a general figure. I think you already saw it again. Okay, and here we have 4 subfigures. Okay, the first one, each figure we show that we use the same data. Use the same data. Is the data is I'm not sure how many data for the black point. This is the raw data. And the red point are our cluster centroids. And for each subcluster, for each subfigure, we use the 64 centroid to do the clustering. Okay, and here we have 4 different methods in 4 subfigures. The first figures use the k-means. So you see the k-means, we can say it's fit the data distribution very well. Okay, so it's k-means. But the disadvantage of k-means is, it usually take a long time, and it consumes a lot of memory space. Okay, it's the main disadvantage of k-means. But the distribution of the centroid can capture the raw data distribution very well. I think this will be the best among all these techniques. And in figure B is the PQ. So remember PQ? You can see here, because it's a 2D data, so you can see how the PQ, we just divide the space into 2 dimensions. Okay, this is the x dimension. We have 8. We apply the 8 k-means. Okay, and along the y-axis, we also apply the 8. The k is 8 k-means. And in total, we have 8 by 8, totally 64 cluster centroids here. But you can see many cluster centroids. Actually, you see here, there's no data belong to these clusters. Okay, so you see that some are empty, and so the distribution of the centroid do not capture the raw data very well. And for figure C, it's called OPQ. Okay, remember the OPQ is optimized. What we call optimized is rotate the data. Okay, so you see the centroids are rotated here. And also we will apply some reorder the dimensions here. Okay, so you see after the rotation, you see I think that the result is still not good. It has the same problem as PQ, because you see basically there are 4 subclusters, 4 clusters for this raw data. But because the OPQ here is also evenly distributed around the space, so even it try to rotate and try to find optimize the rotation matrix, but you can see there's still some centroid. It contains no data. Okay, for example here, no data. So it's a problem as PQ. Okay, the next one is LOPQ. It's called locally OPQ. So in LOPQ, first you apply the k-means. Okay, so assume that you know how many data clusters, how many clusters, how many groups exhibit in this data. Or suppose you know there are 4 clusters. Okay, so you just apply the k-means where k is 4 to do the clustering. is we call the cross quantization. So we have 1, 2, 3, 4. Suppose you perfectly capture the 4 groups of the data, and then you for each group, for each cluster, you then apply the OPQ. So you see in here you have 4 by 4 centroid in each group. In each cluster, you have 4 by 4 OPQ. So in total, there are 16 centroids, and it's also rotated according to the data distribution. So you see here it's rotated. It's rotated based on the data distribution. And so we have in total here, the OPQ also contains 64 centroids, but each centroid is looks like can perfect capture the data distribution. Okay, any problems? Okay, so it's an ideal case, but the requirement is you should know how many clusters is the data distribution for your raw data. Okay, so if you know there are 4, okay, you can run a k-mean square case for to capture each cluster very well. Yeah, but in fact, it's usually not the case. But however, the LOPQ really show a very good performance. Okay, so later we will see do some analysis for LOPQ. Okay, now let us review the LOPQ process. Okay, so there are 4 steps. The first step is when you take the raw data vector, we perform the PCA first. Okay, so PCA is applied first for your raw data. So when you perform the PCA, so actually you can reorder the dimensions according to their eigenvalues. It means the more important eigenvector you should put at the first as a first dimension. And also you can use PCA to do dimensionality reduction. Okay, so in some, if your original raw data is 100 dimensions, so after you apply the PCA, you can reduce it maybe just 20 or 30 dimensions. And usually the performance will not, maybe will improve or will not degrade a lot, just degrade maybe just a little bit, and even sometimes it will be improve your accuracy. Because use PCA you can, by use PCA to do the dimensionality reduction, you can also remove some noise data from your dimensions. Okay, so this is why we can apply the PCA first. Okay, so I think there's some problem in the animation. I will fix it later. Okay, so this means some clusters. Okay, I should be like this. Oh, sorry for the stupid animation. Alright. The second step is do the cross quantization. In the cross quantization, it means given the data set X, and we will do the k-means first. And the k-means is try to divide your raw data into k clusters. Okay, so this is we say when you have the k clusters, then you can you generate the codebook with k centroids, and then you can apply the quantization. For each data, you just see which centroid is closest to the data, then you can assign this data to the cluster. Okay, so it's just a very simple way, straightforward to do the quantization for each data. this data structure given the codebook, and each codebook is associated with an inverted list of the data ID. So this means these data are belong to this cluster. Okay, so this is what we call the cross quantization. Okay, after you apply the cross quantization, you will get a cluster ID for each data. And so each data will be labeled as like this. Suppose it's belong to the second cluster. Okay, so this data will be labeled as this cluster ID. Okay, so it's a coarse label quantization. Okay, later we will hear us other labels. It's for the fine label quantization. Okay, so it's for the next step. Okay, any problem? Okay, for the third step, then we will try to compute and correct the residuals. Okay, so the calculation is like this. Because in the previous step we already assigned each data to its corresponding cluster. Okay, so the residual is computed like this. So given the raw data is subtracted from its central, its associated central, then the result is called a residual. So we just collect all the residual in this cluster. Okay, so here is an example figure. So in our second step, we apply the cross quantization, and then next, after the cross quantization, you can correct the residual for each cluster. Or suppose we divide the data into two clusters. Okay, for each cluster, we calculate the residual of all the data belong to the first cluster, and we do the same thing for the second cluster. All the data belong to the second cluster. We also subtract from it centrally to get the residual. Okay, see here is a calculation like this. Okay, so the final step is apply the LPQ. Okay, so here we just take the residual for each cluster. We take all its residual data and apply the OPQ. Apply the OPQ. So this is basically following the same idea of OPQ we mentioned in last week. Okay, so it's the basic idea for OPQ. And here OPQ will apply the basic step is PCA and do the eigenvalue allocation and find its rotation matrix. Then we can do the fine label quantization. So after we build up the OPQ structure, then when you doing given a query to do the search, so the process is as this. Okay, given a query point y, and the y we want to find is nearest cells, nearest clusters. So here is the example. So suppose I give a query vector y, and the first step is to, here you see there are 1, 2, 3, 4, 5 clusters, and we want to find its nearest cluster. Okay, so suppose we find 3, we want to find 3 nearest clusters. Okay, so here are 3 close clusters here. And then the next step is the query y has to project to each cluster, because each cluster it has its own OPQ setup, right? Each cluster it will have its rotation matrix. remember? Okay, so since we have three clusters, so the first one, okay, we can, for the first cluster, and the y is subtract with the centroid, and then rotate the residual. So when y is subtract from the centroid, we get the y's residual, and the residual have to apply it, given the residual yi, and the yi will be rotated by using the rotation matrix for the ith cluster. Or suppose for this cluster, we subtract from the centroid and then rotate according to the cluster matrix. The rotation matrix is obtained from the OPQ applied in this cluster. Okay, so we then do the rotation, and then we can compute the symmetric distance between the y, the residual of y, and all the candidate in the first cluster. Okay, any problem? Then we will repeat to do the second cluster. Okay, for the second cluster, the y will subtract from the centroid, get the residual, and then rotate according to the second cluster OPQs. Okay, and then we also calculate the symmetric distance. And then for the third, after we compute all these candidate clusters, then we can sort according to the symmetric distance to find out to output your result. Okay, any problems? Okay, so here we give a brief analysis for LOPQ. Basically, LOPQ is very high accuracy. I mean, the quantization loss is very low compared with PQ or OPQ. And OPQ is much better. So the accuracy, the quantization loss, accuracy is very high. Means it's because its quantization loss is very low. Okay, and for a long time, it includes some overhead because you have hierarchical clustering. Okay, so basically it has some overhead when you apply the two quantization steps. And how about the memory it used? Okay, the memory used is calculated like this. Okay, there are three parts of the memory used in LOPQ. Okay, first is K by D. K by D is K times D is your course book size. Okay, so it means, remember in LOPQ we have two quantizations. Okay, so first is course quantization. Okay, so it means you have k-means to apply first. Okay, so in your first quantization, in the course quantization, you generate a cobook. So what's the size of the cobook? Actually, it's K by D. K is the number of the course label centroid, and the D is the dimension, the low vector dimension. Okay, so it's your cobook size is this. Okay. Any problem? And for the second part is called a rotated residual cobook size. Okay, so for each cluster we have applied OPQ individually, right? So for each cluster you have to store the rotation matrix D by D. Remember, D is the dimensions, the number of dimensions. So your rotation matrix will be D by D plus the K star by D. K star is your PQ's cobook. So this is your size of your PQ cobook. It's also called a fine label centroid. The number of your fine label centroids times with your centroid, with your dimensions. And this is the size for one cluster. So in total, you have k cluster. So that's why we have to time with k here. So this is the total size of the rotated residual code. And the last part is the PQ code. It's the data size. It means all the data has been encoded into its PQ code. Okay, so you have n data, the number of your raw data. Okay, and n is your segment, the number of your segment, because you apply PQ here, and the k star is the how many. So with the log k star, you can get how many bits you will use to store each raw data. Okay, so after it's the total size of your each data of your PQ code, because you have n raw data. The number of your raw data is n. Okay, so this is the for each raw data this is encoded. The size is encoded like this. Okay, so the total size can be calculated like this. And so you just sum up all together, you get the total memory used in OPQ. Okay, any problem? Okay, so the memory is really very huge compared with PQ and OPQ. And OPQ consume a lot of memory. So it's the price. Even if the accuracy is very high, but it use a lot of memory to record the detail. And so when your data size scale up to 1 billion, okay, so it will be getting, and you will also use a very big number of the clusters. Okay, so the total size will be very huge. Okay, so that's all for OPQ. And next, I will introduce some papers related to PQ. Okay, so you see, after the PQ published in LPQ is published in 2014. So after that, so the people think, okay, I think PQ is already well developed. So they are almost more than 5 years. There's no related papers talk about PQ. But suddenly, in 2019, CVPR published a paper called Deep PQ. Okay, I think because of the trend of the deep learning, so some scholars they try to apply the deep learning in PQ. So I think this is our first paper. They are addressing this problem by using the deep learning in PQ. But nonetheless, it's somewhat very different to the original PQ. Because the original PQ is designed for unsupervised learning. So you can see through the whole review of the PQ variants, they are all only just use k-means to do the clustering, to do the quantization. So we don't use any label information during this step. But in DPQ is used in a supervised end-to-end learning to learn the PQ codebook. Okay, so I think it's maybe it should not say a breakthrough of the PQ, but they try to give another direction by using PQ to do the classification test. Classification is actually supervised learning. So if you have a label information, So why not we use supervised learning to make the PQ to learn a better codebook. Okay, so the general architecture is displayed here. Okay, so I just copied from the original paper. So it's from the figure 1. Alright, so first, given your data X, I want to generate a good codebook, PQ codebook, and also to quantize X to get a good quantization. Alright, so X is your given input vector. X, and first is embedding, then next, through embedding we will get a very long vector, embedding vector, and we will divide the vector into n parts. This means n segments. Okay, so for each segment, we will have performed the block individually. So this means we will repeat n blocks, but each block will handle one segment. Okay, so this is suppose it's the first segment. In this first segment, for the other segments, we just copy the same architecture to do the training or to do the inference. And for this segment, for the first segment, we see it's Sn is an n segment. Okay, because it already segmented it into a small subvector. Okay, it's a smaller subvector. Then throw another transformation, and then we get the Pn. And then you can treat Pn is a probability of your output. So the probability of here is the k outputs. This means suppose we have k centroids. So you have to set up the number of the k first. The k centroids. So the output of the Pn actually means the probability. This subvector belong to each centroid. Okay, so given the vector Pn and given a vector Sn, and I will generate the probability of k outputs. This means the k. You can throw a softmax to generate k probabilities. Okay, so here are two losses to control your generation of the Pn. So it's called a regularization. So the regularization, including here, is the regularization. Two functions for the regularization loss. First one is called a Chih-Yi batch. Chih-Yi batch is the idea is that in a batch, in a batch we contain many low data, and to do the training. Okay, we hope each data in the batch I can evenly distribute among the k clusters. Okay, so it's formulated, expressed like this. Okay, so this means the probability belongs to the k. Okay, so we hope the probability can be evenly distributed, or not to be only concentrated in one cluster. It should be in your batch. You should contain many diverse, different data that belong to different clusters. So that's why they given a such loss function like this. So if your distribution is evenly among these clusters, so it will be very, will be very low. Okay. If they are concentrated in one cluster, it will be very high. Okay. Okay. So that's why they design the first loss. For the second loss is Chih-Yi sample. This means they encourage the soft and the hard representation to be closer. Okay, so later we will see what is the hard and the soft. Okay, so the main idea is we hope after you do the quantization, we have in here they have two different quantization. One is hard, one is soft. But they hope even you apply two different quantizations, they should be closer to each other. So that's why they give this. Also, if they are very close to each other, so the distance will be this loss will be also very low. Okay, so they give two loss functions to control the generation of the PN. Okay, so after the PN, the probability of the K outputs, and then we will forward it to it. Okay, note that it's called a hard quantization. This step is a hard quantization. Means I will, according to your probability, to see which probability is highest, then I will assign this data to the cluster. So later I will give one hard representation. Okay, so I have a K cluster, but only one cluster will be labeled as 1. All the others are 0. It's called a one hard, right? Okay, so throw the one hard, and you will get only one cluster is assigned to this data. It's called a hard quantization. So here, you see, this step is hard. Okay, so original is a probability, we call it soft. So soft is thrown this way. Soft. Okay. It's called a soft cluster. Soft cluster means I will give a probability for each cluster. Okay, so alright, so it's what we call the soft. Okay, so based on this, I have a hard representation for the data and a soft representation for the data. And then I can use the codebook to reconstruct for the two representation. So this codebook is learnable. Here contain K centroids. So the K centroid is just, if it's hard, this means only one cluster is 1. All the other clusters are 0. So only this cluster, you just check the codebook to reconstruct it to get a hard vector. And for the soft representation, you can also use the codebook, but here you will assign the probability to each centroid vector, right? So you can do the linear combination, okay, to sum up according to the codebook to get a soft vector. Okay, then we have through this, we have through the hard and the soft representation. We then reconstruct them back to the hard vector and the soft vector. And then we formulate two loss functions to do the classification. The first loss function is called joint control loss, joint central loss. Okay, here it's calculated like this. Your hard representation, hard is calculated like this. Okay, and subtract from your soft representation. We hope they are as close as possible. So if they are very close, the loss will be low. And the second loss is called a softmax loss. Okay, so specifically used for the classification. So you just use this vector, use the hard vector and also the soft vector to do the classification. Okay, to just use the vector and output the prediction for your classes. then you will get a cross entropy loss, and it's what they call softmax loss. Okay, any problem? It's a little bit complicated. 好，这样你们听得懂吗？哦，其实它就是说它在做 quantization， 它就分两个 loss， 它分两种 quantization。哦，那一种是做 hard quantization， 是这条 this path is hard quantization， this path is soft quantization. So the difference of the soft and the hard quantization is okay. So just give a simple example. Suppose I have, in this case, I have 3 clusters and give a vector x. Finally, so this path is hard representation will be, suppose the x after I get the set so some transformation I get is a probability representation like this. Okay, suppose I have 4. So I have 4 clusters. So probability belong to the 1, 2, 3, 4 is like this. So what is a hard? A hard representation will be the highest one cluster. So it's this. It's hard. And what is soft? Soft is the same. It's also soft. This is soft. Okay. And when I'm going to reconstruct it, I have a core book. I have a core book containing C1, C2, C3, and C4. I have a core book. This is the core book, the 4 clusters and shores. And when I am going to reconstruct it back, okay, so the x will be the x half will be reconstructed based on C1, right? And for the soft, will be reconstructed like this, based on the soft representation. Plus, okay, so reconstructed like this. Then we hope this should be closed. This is what we call the loss function here. And also we use it. We will use it to do classification. So you just concatenate to the classification head to do classification. You will get the entropy loss. Right? So you just use it to do classification or use it to do classification. Okay, any problems? Okay, so right, this second paper. The second paper is called Differential Optimized Product Quantization. It's published in World Wide Web 2023. Okay, the idea here was just summarize their main their main contribution. Here they propose unsupervised end-to-end learning for codebook. So here is back to unsupervised. And for the data, for each data, raw data X, it will try to decompose it into orthogonal vectors. For example, like this data X, it will be data x here, you see the break vector is decomposed into 3 orthogonal vectors. You can imagine that we have 3 different viewpoints to observe the data x. Okay, so you will get 3 different perspectives, and then do the following. Okay, so you can see we just decompose it into 3 different perspectives, 3 different vectors, and then each vector we just submit, we just overlay into 3 different codebooks. Okay, so this is the first segment. Okay, it's the first codebook, and this is the second codebook, and this is the third codebook. So they are going to deal with the 3 different factors. Okay, so the codebook quantization, we will get their code. Okay, it's for the first vector, second, and for the third, we get their corresponding codes. And when we are going to reconstruct it, we just check their, use the codeword ID to check their codebook to get their vector. And then you just sum up them all together to get your final reconstruction. Okay, so this part is unlike PQ. Because you remember PQ is just concatenation, right? We just concatenate one by one. But in here, what they do is summation. So this part is different from PQ. Okay, but I think it's reasonable because you see X is decomposed into 3 vectors, and you just sum up all the 3 vectors, you can recover the original X. So it's reasonable that at the final, you just do the summation of all 3 vectors. Okay, so it's a general idea of their work. Okay, any problem? And then another contribution is they also propose a differential quantization. It's try to improve, in previous work here, I forget to mention about this one. Okay, this is corresponding to this sentence. Okay, here, this red arrow means it's a non-differentiable encoding. Why? This step from Pn to En, this is a hard encoding. Hard encoding, we do the one part, we will generate one part. So, but the one part is just to pick which one is the highest, right? So you see the 0.6 is the highest among them. So we convert it into a one part vector representation like this. But this process is non-differential. Okay, so this step is non-differential. So it means when you apply the gradient descent, okay, and to this step, you cannot, because it is non-differential for you, so you cannot pass your gradient to the next. Okay, so what can we do? In this paper, they just use called a straight throw. Straight throw means when I am going to pass a gradient to the next, I just pass it. Even in theory, you cannot pass. It's non-differential, but you just forget it. You just pass your gradient to next. Don't care about it's differentiable or not. So this check is called a straight throw. Okay, so you can implement it by using some code. When you implement your model in Python, okay, there are some code you can do several lines to implement a straight throw. Okay, but Okay, so in this paper they use a straight thought to solve this problem, but they think in the DOPQ paper, they think it's not good. It's a straight throw, just ignore the non-differential property, so it's not a good design. So that they propose another way to address this problem. Okay, so this is the whole architecture. Okay, let me illustrate it for you. Okay, so first, you can see there are three main parts. The A part is here. The A part is trying to generate a projection matrix. Okay, so how to generate a rotation matrix? Okay, so given your rotation matrix R, I will divide it into B parts, B segments. So each segment, okay, I will tie with its transpose to generate a rotation matrix. Okay, so here, so remember the rotation matrix is just rotate your vector. So here I divided it into B parts, and so that I can use this technique to generate B rotation matrix. Okay, so after you generate the rotation matrix, then give the input vector x, you just forward it into B rotation matrix. Okay, let's focus on the first rotation matrix here. In the first rotation matrix, okay, you just tie with the rotation matrix with x, and you will get the x1. You can treat this first perspective of the data x. Okay, so you get the x1 here, and you also use the training data to build up your codebook here. You can build a codebook like by using k-means first. And then, so the codebook you can get is probability. Okay, the probability is calculated using you can just use the inner product. Okay, so use the inner product to tie x1 with all the centroids to get your probability. Okay, with the probability, then so the softmax, you get if so the softmax, you get the probability here. Okay, so the probability will be then here we will do the one part coding to see which one. Suppose after the one part, after the softmax, you get a presentation like this. You get your probability like this. Okay, so one part, you get the representation like this. So it's the same process. Okay, so here you will find, okay, you belong to this cluster. So only this cluster is set to be 1. All the other clusters are set to be 0. Okay, so this is the process mentioned here. Then when you are going to do reconstruction, you just look up your codebook to reconstruct it. And we hope the reconstruction should be close as your original X. So here is the quantization loss. And there is another loss called the reconstruction loss. The reconstruction loss is we just summation all the 3 blocks. And in total we have B blocks. Okay, we just sum up all their reconstruction vector to generate your reconstruction. And the reconstruction should be close as your original X. Okay, any problem? Alright, so here is their second contribution they mentioned here. They said such a one-part encoding is not differential. So the previous paper. Okay, so instead of using the straight law, okay, here they propose another called direct loss to estimate the gradient passed to the next block, to next layer. Okay, here is the derivation to do the direct loss. Okay, so actually they use the reinforcement method to do the derivation to find what is the direct loss to be passed, the gradient should be passed to next. Okay, so I will just give this step and they just show from the solar experiment to show that this direct loss is really more effective than the stress law. Okay, any problem for the second paper? This is the third paper. This paper I prepared in this lecture. Okay, this paper is published also in CBPR 2023. It's called a disentangled representation learning for UNQ. And what's the UNQ? UNQ is a paper published in ICCB 2019. So it's called unsupervised neural quantization. And what is this? And UNQ can be formulated in this. It's a very simple architecture step for UNQ. Okay, UNQ works like this. So given a vector x. Okay, so this is a database vector x. And we have it's an encoder-decoder architecture. So we hope to quantize your original data, the raw data vector, and so that we can store a compact representation, a quantized version of data x. Then, when we want to use it, we use another decoder to reconstruct it. And we hope the reconstruction of x should be close as your original data x. Okay, so the basic like an autoencoder. We have a encoder, decoder, and we hope the output should be as close as your original. And then in this design, we have the encoders like this. It's a linear, Maginot, and ReLU, and repeat twice. Okay, and then after it, then we will get this representation of the data x. And in this representation, and we will use this representation to several different codebooks. So we will build several codebooks, and these codebooks is based on here we will do for each codebook we will do the quantization. So here you see here we locate it here. We will find which code word is closest to the data x, and this is the codebook we use. Code word we will use to store it, and in the second space, okay, we will get its closest code word is here, and it's the last codebook. Okay, here we find this data x is close to this code word. So we will use this different code word to represent data x in different space. So you can treat it like multi-gate. You just project the x to multiple different spaces. And then in different space you will quantize it. And to do the quantization to get different code words. Then finally we will summation them together to do the generation, to decode it. Okay, when you do the decode, you just repeat the same architecture you have a linear, Bayesian, and repeat twice. Okay, use this to reconstruct it, and we hope your reconstruction will be close to your original raw data. So it's a general process for U and Q. Okay, so U and Q is they try to use deep learning, autoencoder architecture, okay, to use it to do the quantization. But in this paper, they try to define that. Okay, so if you use the UNQ directory, you can do it better. And they propose to disentangle the class center and the residual first. Then do the quantization. It will achieve a better result. So the idea is like this. So please recall what we have taught in coarse level clustering and fine level clustering. So remember in LOPQ, we say there are two-step quantizers, right? So first is a coarse, and the second is a fine level PQ. Okay, they just adopt this idea. So they say maybe we should do the data clustering first, and to do the coarse level clustering. Okay, so this is the idea in the original space. In the original space, you can divide and you can perform the k-means first. So that we generate 3 clusters. Each cluster, we get the cluster central here. You see the triangle. This is the cluster central. Okay, so here we have a coarse level cluster central vector here. And for given any data, suppose this data, and this data we can subtract because it belongs to this cluster. Okay, so we can subtract it from its central to get its residual. Right? So it's the same process. So this means we get the coarse the cluster central vector and also the residual vector. So before they are combined, they just add together. But now we disentangle separately into 2 different vectors. So 2 vectors. One is the class central vector, and the other is the residual vector. We just concatenate, not add them. We just concatenate into 2 large. Concatenate the 2 vectors together. Okay, so throw the encoder, and the length is repeated twice. And then here we see, because here now we will regard it as a disentangled representation. So in this representation, you can think about, we just use for this, there are 3 different clusters in this cluster space. Okay, we use their residual, and we use the residual to do the fine level quantization. Okay, so here we generate this cohort like previous like PQ. Okay, we do the quantization here. Okay, fine. Okay, suppose the residual vector, because of this data X is belong to the first cluster. Okay, and in here we will use this residual to quantize to this cohort. So this the quantization is represented like this. Okay, it belongs to the first cluster, and in here it belongs to the second cohort. Okay, then we use it to do the reconstruction. So the decoder is the same, similar module is the encoder, and repeat twice, and we will reconstruct it into here. Then we compare the distance between the reconstruction with the original one. So basically, it's also auto-encoded, but they apply to separate the vector into two. One is the cluster centroid vector, and the other is the residual vector. Okay, so here to do the encoding, it will consider the cluster centroid and also residual vector. Together, they will consider the two vectors together. And in your decoder, they will also, you see, the cluster centroid vector will also pass to here. And here, you will concatenate with the residual reconstruction again. Okay, so this idea is also very simple. You just divide, decompose the original vector into a cluster vector and the residual vector, and to do the encoding and decoding. So it's just this, like this, but they also show that this entangled process can make your construction better, because you just in your encoder decoder, you just need to focus on the cluster residual space. So it's make your neural network your deep learning module can focus on your residual space, not a large original space. You can focus on your residual space. Residual space is usually more compact, and they usually follow the Gaussian distribution. Okay, so intuitively, your deep learning network can learn better in the residual space. Okay. So the general concept of the idea. Any problem? Okay, so you see, even a very simple idea can publish in a top conference. So in today's lecture, we saw there are such examples. All right, so there are other techniques. Unlike PQ, here we just mentioned some of them, like for example, additional quantization, AQ, or the composite quantization, called CQ, and the residual quantization. And all these methods, they are based on just sum up all your vectors together to reconstruct it back to generate the reconstructive vector. So all these are based on addition. Unlike PQ is concatenation, right? We just separate the original vector, and then finally we will concatenate one by one to reconstruct it. But for AQ, CQ, or RQ, they have a different operation. They have to sum up all these vectors back to reconstruct your vector. So they are following the addition to do the reconstruction. Okay, so I hope maybe next time when I introduce PQ, I can introduce the newest papers published for the residual computation. Okay, but not today. Okay, so here is the oral reference I mentioned in today's and last time's lecture. Okay, so that's all for